Hi everyone. Can I'm seeing that everything is good here, but when I start these streams, I'd appreciate if someone just writes in the chat that they can hear me to make sure that everything is working. I mean, I get the green light at my end, but you never know what might be happening. So if people can hear me, I'll start, and then just someone in the chat say, you know, uh, tell me if everything's good. Yeah, thank you very much. All right. So what we're going to do today is like we did last time is we're just going to go over the material that you watched in the pre-recorded videos, and you should have watched two pre-recorded videos. One is on um, 1D kinematics under the assumption of constant acceleration, and the other one is 1D kinematics but for simple harmonic motion. Okay, and I've got two questions that we'll go over today, and I'll leave you with two questions that you can practice on your own, and then you can ask me either through email or through the Google Hangouts that I do every evening, whether you did it right or not. And of course, next week you'll have an assignment on this, and you can ask questions on that assignment as well. So these assignments, they come up in Canvas as quizzes, but I simply set an unlimited time. So, you could start the quiz if you have a question, then, just catch me online in the evenings and let me know or just ask your question. Also, I have been doing these Google Hangouts in the evening. They're really nice. Unlike the live chat here, there's no lag at all, very little lag, and if 7:30 doesn't work for you, let me know. I mean, I can make myself available at other times, but for a lot of people, they tend to like the 7:30. That's what I found last semester, so I just continued with it this time. But if for some reason 7:30 is no good, then just let me know and we'll do things. Okay, so the two questions are one question on constant acceleration and the other question on simple harmonic motion. And the reason I want to do this in this less formal style so that you could see me actually work through the problems and ask questions as I do if you have any, how you do things, how I do things. And in particular, I want to show you how to draw the diagrams because in the pre-recorded videos and in my notes, I have diagrams which are finished. Okay, you don't see the layers in which I do things. And so that's why I wanted to do these live streams to augment what you're seeing in the uh, recorded lecture, pre-recorded lectures. Okay, so let's take a look at this first problem. This first problem, there's a skyscraper, and I drop a rock. So a rock is dropped from the top of a skyscraper. It is found to be falling at 10 meters per second when it passes the first window, and then 50 meters per second when it passes the second window. Okay, so you can picture that in your mind. I drop a rock from the top of a skyscraper. Usually on tests or assignments, I'm very precise with the language. Here I say I drop a rock. I don't throw it up. I don't throw it down. So I would actually probably more explicitly say something like drop a rock from rest or release a rock from rest so that there is no velocity associated with it. But this is good enough for our purposes today. And so you read that, and then of course read what I'm looking for. So I ask question A: how far apart are the two windows? So there's enough information here to figure out how far apart the two windows are, and how long does it take the rock to fall between the two windows? Okay, so the way you start these problems is I'm going to switch to another whiteboard is by drawing the picture, but you draw the picture in three stages. The first stage is just draw like a raw picture of the scenario. Okay, so here I am switching to a whiteboard, and let me do this part of it in black. So you'd say, well, there's a skyscraper, there it is. Okay, and there's ground level, and there's a window here. Uh-oh, for some reason, oh, something just happened. 1 second while I try to fix what just happened. Oh, Pinta crashed. Yeah, well, every once in a while there's a little bit of technical problems. Give me just 1 second. I just had a crash here. It's never happened before, actually, interestingly enough. This should not take me long, but um, live streams and open with. Wow, I've never really had that before. Okay, let me see if you're seeing that. Yeah, okay, now you're seeing that, but let me start over. Let me create a new fresh one. That was very strange. I've never had Pinta crash. Pinta's the tool that I'm using as my whiteboard. I've never actually seen that happen before. Okay, so let me start over. Start off by drawing, the building here like this, the skyscraper. And there are two windows. There's a window here, okay, like that. And then there's another window here like that, okay. And call this window number 1 and window number 2. And, I'm at the top here. So here's a rock. And then I release the rock and it falls down like that, okay, to the ground. All right. And of course, it passes window 1 and window 2. All right. So, that's just a raw drawing of the physical situation. What you should be doing when you're drawing these things is think of them as like actually doing an experiment. So there's our experimental apparatus. But now, before we try to plug into the equations, because we're going to get numbers off of this diagram, before we even try to plug into equations, we got to do some measurements on this. Of course, this isn't a real measurement in the lab, but just imagine that you're doing a measurement. We got to measure distances and times. So to measure distances, you're going to need a ruler. So to do that, we'll add a coordinate system, an axis here. Okay, and so I can put the axis here like this and going straight. Oh, that's terrible. Undo. Let me try that again. A little bit better. Okay, like that. And so this is going to be like a ruler. I'm drawing it as just like an x-axis, and up is going to be positive. Okay, and you could choose down as positive, but I think it's probably best if we all stick to the same convention. Let's make up always positive and to the right positive. If this were a horizontal axis, then we'll just make things that moving to the right positive and things to the left negative. You don't have to do it that way, but there's no reason to not do it. Not to adopt that convention. As long as you're consistent, it would work out. Okay, so there's our ruler. Now, I'm not going to put gradations on it, like little ticks on it, but there's the ruler, but I do have to show you where the origin is on the ruler. So we have to choose a point which is the origin. And you say, can I choose it on the ground? Yes, you could choose it at the top here. You could choose it anywhere. This is like the 0 of the ruler. But if you choose it on the ground, then you're gonna have more unknowns because you don't know the height of window 2 and you don't know the height of window 1. And what you want is the difference between the two heights. That is how much higher window 1 is over window 2. And so, choosing your origin on the ground is probably not the best choice. Choosing it up at the top is not the best choice. Either you could choose the origin at window 1 or window 2. Both would work just fine. I'm actually going to choose the origin right here at window 2. And so that's where the 0 of the ruler is. You get to make that choice because, again, imagine you're measuring like a tabletop or something. Where you put the 0, that's up to you. Okay, you can put it flush with the edge of the table, or you can move it around and then just subtract a couple of numbers. So you get to choose this, but I think this is a convenient choice. I think you'll see that as I go along. You could have chosen it at window 1. Someone in the other class said, can I choose it at window 1? Yeah, sure. The numbers would be different, but your final answer would be the same, actually. Okay, so there it is. There's our 0, and I'm not going to put like little ticks there because I don't know how big these distances are. But there's one other thing you got to choose, and that is where is t equals 0. Okay, so you have a stopwatch. Imagine that you're doing an experiment and you have a stopwatch. At what point are you going to press the stopwatch, and that's going to be your 0? And I'm going to choose my 0 right here. That's my t equals 0, not my x equals 0. And oh, that's terrible. Hold on, let me try to draw that again. All right, there you go. That's a little bit better. T equals 0. I'm going to choose t equals 0 right when the rock passes window number 1. Okay, so that's where t equals 0 is. Okay, the time down here, that's some later time. All right, like that. Okay, so I've chosen a point which is 0 in space, and I've chosen a 0 in time. And now we can start to measure things off of those two. But before I do, let me go back to the problem, okay, and let me actually copy and paste the equations that we're going to put the numbers into, because the whole reason for doing this diagram is to measure or identify the numbers that we're going to put into the equations. And the equations are the ones that I discussed in the pre-recorded lecture. It's just basically these 3 equations here. All right, so I'm going to do it like this. All right, there you go. I just cut and paste the equations in there. So we have equation number 1, and it's basically your position as a function of time. So on the left-hand side, you have x. I could have written x as a function of time, but I think at this point it's understood. So here's x as a function of time because there's t in there, okay? And equation number 2 is the velocity as a function of time, okay? And then finally, equation number 3 is basically equation number 1 and 2, okay? It's equation 1 and 2, but with the time eliminated between the two, okay? So I didn't do that arithmetic. It's kind of easy. Just like isolate t here, plug it into number 1, and number 3 pops out. But this is important to realize that number 3 doesn't have time in it, because if you've got a problem, 1D kinematic problem, and there's no time in it, equation number 3 is the one you want to go to, okay? Before I switch back, let's look at what variables you're looking for. What things you're trying to find, okay? So in equation number 1 here, let's look at the variables in there. There's x naught. X naught is the initial position. That's the position when your stopwatch reads 0 seconds, okay? So that's your initial position. The final position, that's the position at a later time t. So if you wait a time t, you're going to be at a different position, usually called the final position. That is given the variable x, okay? So x naught is the initial position, x is the final position, okay? There's also v naught and v. V naught is the initial position, and v is the final position, okay? And then there's 2 more variables. Time, okay? And that's the time after the stopwatch, after the 0 in the stopwatch, okay? And there's a. And a is the acceleration. Now, I don't give you the acceleration in here, but you actually know it because it's the acceleration due to gravity on the surface of the Earth, okay? And the acceleration due to gravity on the surface of the Earth is 9.8 meters per second squared, okay? Now, that is the correct number. There's some more decimals, but it actually varies depending on where you are on the Earth. All right, but for the purposes, and by the way, that's what you should use in the lab. I think your lab number 3 or 4, I don't remember now. It's one of the labs that you'll be doing soon. You're actually going to be measuring g. You're going to be measuring the acceleration due to gravity, and you better get a number like close to 9.8. Okay, but for the lecture and throughout, all of the lecture this semester, we're just going to approximate a as 10 meters per second squared, okay? And that is a little bit of a kludge. I mean, it's like a 2% error. That's pretty big, actually. But you know what? It makes the arithmetic so much easier, and so it's fine, okay? And we'll do that. And on a test, I'll probably give you constants on a test, but, memorizing that the acceleration due to gravity is 9.8 meters per second squared approximated to 10, that's pretty easy to remember, okay? So you do know the acceleration as well. Okay, let me switch back to my whiteboard here, and let's see if we can identify off of the diagram the various values that we need to plug into equations 1, 2, and 3. And you could go through these systematically. So you could pick start off with x naught, okay? And what's x naught? X naught is the initial position. That's the position at t equals 0. Well, here's t equals 0. Where is the thing at t equals 0? Well, the rock is right there. And so there's your x naught, okay? But you say, well, let me read that off of my ruler, and you don't know. It's just you don't know how, you don't have any gradations on this ruler, and you can't put any on there because you just don't know how far apart the 2 windows are. After all, that's what you're trying to find. That's what the problem is trying to find. So we don't know what our x naught value is, and so what we can write here is just x naught is equal to question mark. In fact, that's what we're going to be solving for, because x, which is the final position, is down here, okay? And that, by definition, is 0. So you're over here at x naught at t equals 0, and then at some later time t, you're at x is equal to 0, okay? And so there's your final position, all right? So you got your initial position and your final position, all right? And next, you might do the velocity. So you got an initial velocity, and you have a final velocity. Now I give you these numbers. I told you that the initial velocity was, I won't switch back, but if you look back, you'll see that I told you it was 10 meters per second. Okay, like that. And I told you that the final velocity was 15 meters per second, like that. Okay. But we have to be very careful because there's a direction. Okay. So if you're at window 1, which way is the rock falling? Okay. Remember, I didn't throw it up or down or anything like that. The rock is actually falling down. But down is a direction, And in our diagram, up is positive, so down is negative. So when you get the numbers out of the word problem, don't just blindly plug them into the equation, and don't just like, write it down. Oh, the initial velocity is 10. Think about very carefully in terms of the coordinate system, that is in terms of the blue, the arrows and the time, the sorry, the the x-axis and the time. Think about, what you would actually measure there. Okay, so x naught we don't know, but the velocity would be going down, and so it's actually negative. All right, and same thing over here at window number two. At window number two, it's also going down, but at 15 meters per second, but still negative. Okay, so this is the order I go in: initial position, final position, initial velocity, final velocity. Acceleration, I already gave it to you, but once again, let's think very carefully about the sign. Yeah, it's things that fall accelerate at 10 meters per second squared, but they don't accelerate up at 10 meters per second squared. That would be very strange if everything fell up. Things fall down at 10 meters per second squared, and down is negative. Okay, so notice that both of our velocities and the acceleration have to be negative. Okay, and then finally the time, that's the time at window number two. That's like our final time. That's unknown. Okay, and this is pretty much a complete diagram. So you can see there I used color to indicate the order in which you would draw the diagram. First, just draw a picture of the physical situation. Secondly, put an x-axis there, which is your measurement of x, and put a time there, okay? And of course, you can't really draw time, but you could draw where t equals 0 is, or where the object is at t equals 0, okay? And then read off of the diagram the values that you're going to be substituting into the equation. That is x, x naught, x, v naught, v, a, and t. And now you're ready to substitute into the equation. Okay, so we're going to switch back. Let me look at the chat to see if there are any questions. At any time, if you have any questions, just type it into the chat, and I'll eventually look over and see that you've typed something. Now, I might answer your question a little bit after you asked it, but I'll eventually get to it. Okay, so so here are the equations, and let me just quickly cut and paste the values that we found from the diagram. All right. And I'm sure you guys are writing this down, so I'll actually go slowly. I know that cut and paste was pretty fast, but let me get rid of this. You don't need that. Okay, so we had that x naught was unknown. Okay, we have that x was equal to 0 from the diagram. We had that the initial velocity v naught was negative 10 meters per second. We had that the final velocity was negative 15 meters per second. We have that the acceleration was negative 10 meters per second squared, approximating the 9.8. And also, I didn't write it down here, but let me add also the time is unknown. Okay, like I didn't tell you how long it takes for the rock to fall from window 1 and 2. In fact, that's part B. Okay, that's part B. So there you go. There are the numbers, and so this is why I recommend that you do it in the order that I told you. A lot of students will just look at the word problem, and they'll just try to get some numbers and substitute it into the equations. And if you do that, you're going to make lots of mistakes. Like, you may confuse the initial and final position here. You may confuse the initial final velocities. You may get the signs wrong. Okay, so there are lots of little things, little subtle things you can do. Drawing the picture is like trying to picture in your mind exactly how you would do the experiment, and then you can still make mistakes, of course, but the tendency to make mistakes are much fewer. Now that you have all those numbers there, you've got all those values, okay, and you want to solve for x naught, you take a look at the three equations, and you have to decide, can I use equation 1, can I use equation 2, or can I use equation 3? Well, the equation you use had better have x naught in it, otherwise you can't solve for x naught, so that eliminates equation 2, and also you don't know the time. Okay, and so that eliminates equation 1. There's only one possibility. It's equation number 3. Okay, so we're going to take equation number 3, and we're going to substitute the numbers into it. Okay, again, I'm cutting and pasting, so I'll explain slowly what's happening here. So if you're taking notes, hopefully I'm not going too fast. If I am, just slow me down in the chat. Don't be afraid to say, hey, slow down. So here's equation number 3. I just rewrote it. That's v squared is equal to v naught squared plus 2a x minus x naught. All right. And we can go ahead and substitute in. For v is the negative 15. Okay. And I'm not going to put the units in there because I made the problem easy in the sense that I just gave you all the values in MKS units. Okay. So it's negative 15 and squared. And then for v naught, it's negative 10 squared. Whoops, I forgot a squared in there. Let me put that in. There you go. Okay, so negative 10 squared plus 2 times a. A is negative 10 times x minus x naught. X is 0. X naught, that's our unknown. Okay, and so here we have, well, 15 squared is 225. 10 squared is 100. 2 times negative 10 times negative x naught. Notice there are two negative signs there. So the two negative signs multiplied with one another will give you a positive. So you get 225 is equal to 100 plus 20 x naught. You know how to rearrange equations, and that'll give you that x naught is equal to 6.25 meters. Okay, so that's where x naught is. All right, let me look in the chat if there's any questions. I have to switch windows when I look, so no questions so far. All right. So there it is. There's our answer, 6.25 meters. Let's go back to the whiteboard and take a look at where that would be. So here, let me do this one in green. So here's our 0 on the ruler, and that's where window number 2 is. Window number 1, that's where x naught is, and we found that x naught was 6.25 meters, like that. 6.25 meters, and that answers the question because window number 1 must be 6.25 meters above window number 2. Okay, so there we go. That's question A answered. I had a second part. Let's take a look at that. All right, the second part was, how long does it take? All right, for the rock to fall between one window and the other. Now, in part A, you could only use equation number 3. In part B, you could actually use equation 1 or 2. Let me show you why. You're solving for time, right? So you can use equation number 1 because you know everything in there. Now you know x naught. The only thing you don't know is t. And you could use equation number 2 because you know v naught, you know a, and you know v. And so t is the only unknown. Okay, and so you can choose either 1 or 2, but I think it's pretty obvious you want to use number 2 because it's a linear, and number 1 is a quadratic. Okay, so we don't have to use a quadratic in this particular problem. In general, you will. Okay, now I wanted to give you something that was a little different than what I did during the pre-recorded lecture. In the pre-recorded lecture, you saw that in the problem I did there, where I went, I answered about as much as you could possibly answer for that question, okay, in terms of 1D kinematics. We did have to solve the quadratic equation. And the practice problem that I'm going to give you will actually also require you to solve the quadratic equation. So question number 1 here is it covers everything, but except for having to use the quadratic equation, which in general you may have to. All right. So okay, so we're going to use equation number 2 here to solve for the time. So let me get that in there. All right. Okay, so we decided to use equation 2. Equation 2, I just rewrote it here. V is equal to AT plus V naught. Okay. V, that's the final velocity. That's the velocity after time t. That's negative 15. The acceleration, negative 9.8. But again, we're rounding it off to negative 10. Okay. Times t, which is what we're solving for. And then V naught was negative 10. By the way, it was just a coincidence that A is negative 10 and V naught is negative 10. If I were to do this problem again, I'd probably change the numbers just so that the coincidence doesn't confuse you. But, A is negative 10 because that's the acceleration due to gravity. And V naught is negative 10 because I told you that's what you would measure the velocity as when it passes window 1. Okay, while solving for that, you just get half a second. Okay, so it would take a half a second to fall from window 1 to window number 2. All right, let's look at that on the diagram and see if the answer makes sense. And also it'll show us a little bit what acceleration really means. Okay, so here we are back at the whiteboard, and take a look at the velocities, the initial and final velocity here. The initial velocity is negative 10 meters per second. The final velocity is minus 15. So it's sped up as you go down. So velocity is how fast you travel. Acceleration is how much do you speed up per unit time, or at what rate does the velocity increase or decrease? Well, here the velocity is increasing from negative 10 to negative 15. Well, I say increase, I know it's becoming more negative, but in terms of absolute value, it's falling faster at 15 meters per second. Okay, and we know that the time in between the two here was 0.5 seconds. In other words, half a second. Okay, well, take a look at what the acceleration is. The acceleration is negative 10 meters per second squared. So what does this meters per second squared mean? You could actually rewrite this as negative 10 meters per second, and then the whole thing per second. Okay, so what that means is that this acceleration says that the velocity is going to increase. I say increase, but you know what I mean. It's becoming more negative by 10 meters per second every second. Every second you can expect the velocity to be falling down by 10 meters per second more. Okay, now that's in 1 second, right? What if it were only half a second? What if you only waited half a second? Well, you don't have enough time to actually build up to the full 10 meters per second extra. So in half a second, you'd expect that the velocity increases by 5 meters per second downwards. And that's exactly what you're seeing here. If you're at 10 meters per second down, half a second later, you're at 15 meters per second down. Okay, so that's the meaning of the acceleration. And I set up this problem just so that to try to make it as clear as possible what acceleration means. Okay, it's not how fast you're going, it's how much the velocity is either increasing or decreasing over time. Okay, and that per second squared, you could think of it as meters per second per second. It tells you how much the meters per second increases every second. Okay, all right. That's it for that problem. Let me look in the chat if there's any questions. Okay. All right. People are looking good. So let's move on. Let's move on to question number 2. Question number 2 is, I think, mathematically easier, but conceptually maybe a little bit more demanding because it's a simple harmonic motion, and it's 1D simple harmonic motion. So what is simple harmonic motion? It's where you have something that vibrates back and forth like that. Okay, so just anything that vibrates back and forth along the line, 1D. Okay, and you say, well, what does that? Lots of things. So many things it's hard to imagine them all. Like, for instance, I don't know if you know this, maybe as a biology majors might know this. Inside of our ears, we have these little fibers called cilia, and they vibrate when sound goes in our ears. That's how we can hear, because the vibration of the cilia stimulates the nerves that send a signal to our brain, etc. And so the way you're hearing me now is because of the vibrations of the little hairs inside your ear. Okay, those little cilia. All right, so there's one example. Another example is you could take a pendulum, just a string, tie a rock to it, and it swings back and forth. Or you go up to something that's a little bit unstable and you knock it, and it wobbles back and forth. Okay, all of those are examples of harmonic motion, simple harmonic motion. Okay, now it's actually simple because I'm assuming that the wobbling will never die down. Okay, so that it just keeps wobbling back and forth with the same amplitude forever. In reality, it'll, eventually the wobbling will decrease and then it'll dissipate out. Okay, but that's why we call it simple. It's not simple because the math is simple. I mean, when we went through the math, you saw that I had to actually differentiate sine and cosine functions, and that's always a lot of fun. But it's simple in the sense that there's no extra things going on except just the oscillation. There's no damping or anything else like that going on. Okay, and so this oscillation goes back and forth, and there's a few things you can say about this. There's some properties. One, the motion is symmetrical about the origin. So if this is the origin, we'll call that x equals 0, also known as equilibrium. The oscillator will move as far to one side as the other. Okay, so it's like if you put a mirror there, the same motion on the one side occurs on the other side. Okay, so the motion is symmetrical like that. All right, and there's a few maximas that occur. One of them is the maximum displacement from equilibrium. That's how far does it travel to one side before it stops and turns around, okay? And that maximum displacement is called the amplitude, and it's given the symbol capital A to distinguish it from acceleration, which is little a, okay? And so that's one maximum value that's obtained. Like x varies, but it doesn't vary forever because otherwise it would just go off. X gets to a maximum amount and stops and turns around, okay? And so that's your amplitude. There's a maximum velocity, okay? At the endpoints, it actually has to stop because, one instance it's moving to the right, the next instance it's moving to the left. And so between positive and negative, moving to the right and then moving to the left, it has to pass through zero. So the velocity at the endpoints is zero. The maximum velocity is obtained as it passes through equilibrium. Okay? So maximum velocity occurs at equilibrium. And then, of course, there's a maximum acceleration. And the maximum acceleration occurs at the endpoints because that's where the oscillator stops and it swings it around. That's when it's being swung around the fastest, whatever the object is that's oscillating. Okay, so I've got a diagram for that at the end, but just a quick summary right now. Maximum displacement is at the endpoints, maximum velocity is at the middle or at equilibrium, and maximum acceleration is also at the endpoints. Okay, these maximas are related to one another, and they're related to one another through the angular frequency, and the angular frequency is determined by the period. Okay, now angular frequency is kind of a weird concept because it's not something that you measure in the lab, but the period is. Okay, and as soon as you have the period, you can immediately calculate the angular frequency because the two are related to one another by a very simple formula, which I'll just give you in a second. Okay, so the period uniquely determines the angular frequency and vice versa. And so here I tell you that this thing has a period of 4 seconds. And what the period means is it's a time for one cycle. So if you start the oscillator on one side here and you let it go and it goes back and forth like that, and the whole cycle takes 4 seconds, so like 1001, 1002, 1003, 1004, and you're back to where you started, that's a period of 4 seconds. And the symbol for the period is capital T. Okay, so these are the properties of the simple harmonic oscillator that I'll ask you questions about. Maximum acceleration, maximum velocity, maximum displacement, also better known as the amplitude, angular frequency, and period. Okay, and they're related to one another. All right, let's go through the questions. So the first question is, at what point in the cycle does maximum acceleration occur? I just answered that. Okay, so it's at the end point. Okay, or end points. All right, so there you go. And then the next question is, what's the angular frequency? So the angular frequency is uniquely determined by the period, and it's given by this formula right here. Okay, let me actually cut and paste the whole thing right there. It's actually given by that formula right there that you see highlighted. Okay, now the symbol for angular frequency is actually omega, which is the last letter of the Greek alphabet. It looks like a W, but it's got rounded bottoms. Okay, rounded bottoms like that. All right, and I can't do, this is just a simple text editor. I can't do, maybe I'll look later afterwards. I'll try to see if I can find a better text editor, but I can't do an omega right now. So I'm going to do a W, but it is that kind of rounded, should have rounded bottoms. Okay, so omega is going to equal 2 pi divided by capital T, 2 pi divided by the period. Okay, well, pi is just 3.14. The period, I give you that in the problem, it's 4 seconds. And so the answer you get, actually, let me put the seconds in there so you can see what units come out. Okay, so I tend to drop the units if they're MKS in the formulas, but I can put them back in. So I've got 2 times pi divided by 4 seconds, and the answer is 1.57. Notice that the seconds is in the denominator, so it's not seconds, but it's per second, or 1 over seconds. Okay, so that's the units. All right, now that's perfectly fine for this course, and like in any physics course, people will generally write 1 over seconds. But if you ever I don't know, wind up working in a lab or something where you have instruments and the instruments measure frequency, you will, on the instruments, you will hardly ever see 1 over seconds. Instead, you'll see hertz. Okay, now hertz, HZ, like that is the symbol. Hertz and per second, 1 per second, exactly the same. Okay, I don't know. It's just a historical thing, and so I have to mention it because in the future, if you see an instrument that measures frequency, it won't show what per second. It'll actually show hertz. Okay, so I don't know if anyone listens to music on the car radio anymore, but you can um, tune your car radio to different frequencies. So if you tune to 94.5 FM, if you look, that's 94.5, and it'll actually say megahertz. Okay, that's millions of cycles per second, so millions of hertz. Okay, so yeah, that's all that hertz are, and for our test, you should know both. You should know both. Okay, although the per second is more practical because it's more obvious how the units will blend together. Okay, so there's the answer for the angular frequency, and these other maximas, the maximas that I told you about, amplitude, maximum velocity, maximum acceleration, they're all related to one another with omegas in front. Okay, so let's do the first one, amplitude, and so that's one of the maximas. And did I give you another one of the maximas? I did. I gave you maximum acceleration of 50 meters per second. I know it's clipped off there, but that's all you need to see. Maximum acceleration is 15 meters per second. Okay, so you know the maximum acceleration. You now know omega, and you're asked to calculate the amplitude, and you say, okay, what formula do I use for that? And it's this formula right here. Okay. A max is equal to omega squared times A. Okay, so there it is. So that relates, this formula here relates your maximum displacement, in other words, the amplitude, and the maximum acceleration. And you'll notice that the two are related to one another through this omega squared, or through omega. Okay, now we're asked to solve for the amplitude, and so you need to isolate the amplitude here. So just divide both sides by omega squared, and you get that capital A is equal to A max divided by omega squared. Substitute in the numbers, and you get 6.09 meters per second. Okay, that is the answer, and the units will turn out to be MKS because everything else was MKS. But let me show you that the units actually work out here. Let me put the units in there, and just so you can see that the units actually do work out. That 15, okay, that was your acceleration. That was meters per second squared, like that. Okay, so there's one of the units that I dropped and put it back in there, and here's the other one. That omega has units 1 per second, like that. Okay, so here's the other unit. Now if you take a look at this, you go, well, how does that give you meters? Well, notice this whole thing is in the numerator, and this whole thing is in the denominator. So in the numerator, we have a per second squared here, like that. There's a per second squared there, like that. And in the denominator, we have a per second, but then that's also going to be squared. So we have a per second squared divided by a per second squared. The seconds drop out, and all that's left are the meters. Okay, so this equation here, maybe it's helpful to know the units because that's why it works. Okay, so doing the units in a slightly different way, or thinking through the units in a different way. A is meters, omega is per second, but then it's squared. Okay, so from here we're getting a per second squared, from here we're getting a meter, so the whole thing is a meter per second squared. Meter per second squared, that's exactly what the acceleration is. Okay, so yeah, the units work out here, and there you go. You get an answer of an amplitude of 6.09 meters. Okay, what's the next question? What's the maximum velocity? All right, so this is another one of these where I'm relating a maximum to another maximum, but this time we're relating the maximum maximum velocity to the amplitude. Okay, and here's that equation. Okay, so here's the equation before I substitute in any numbers. We've got that V max is equal to omega times A. Okay, so A max is omega squared times A. V max is just omega times A. Okay, and omega we know is 1.57. A is 6.09. Multiply the two together, and you get that the velocity is 9.56 meters per second squared. Okay, and that's the answer. Let me just show you that the units work out again. This one's a little easier to see. The 1.57, that's your omega, is per second, and your amplitude is meters. and they're backwards. But what do you get if you have a meter per second? A meter per second, that's a velocity. Okay, so the units work out there. Okay. Finally, I ask, at what point in the cycle does it occur? I should probably, just to be very careful, and on tests, by the way, I'm very careful with my language. So at what point in the cycle does this velocity, or probably maximum, does maximum velocity occur? Like that. And the answer is maximum velocity occurs at the middle. Okay? Or you could say at equilibrium. Or you can even say it at x equals 0. They're all equivalent the way we've been doing things. All right. Let me look in the chat if there's any questions on that one. That one's pretty easy. Generally speaking, you don't need to draw a diagram for simple harmonic oscillators. You just need to be very careful in reading the problems. So for example, question D, I could have asked it in a slightly different way that might have made it more tricky. Now, I never try to be tricky in my problems, but I got to make sure that you know how what the words mean and things like that. So over here, instead of saying what is the maximum velocity, I could have asked the question for part D, what is the velocity at equilibrium, like that. Now, suppose you didn't know that maximum velocity is at equilibrium, or conversely, the velocity at equilibrium is the maximum velocity. If you didn't know that, you would not know to use that equation. Okay, so it is important to know at which point in the cycles your various maximas occur, and just so you can identify, things like this. Like here, I explicitly said at what point does the maximum velocity occur. Okay, and there's only two possibilities, either in the middle or at the endpoints. Well, maximum velocity, it's in the middle. Okay, but I can make that question a little bit more subtle. I could say, what is the maximum? Sorry, what is the velocity at equilibrium? And then you've got to know in your head that I'm talking about the maximum velocity because that's the velocity that's obtained at x equals 0. Okay, let me switch back to the other whiteboard. I want to show you a diagram that shows where all these different maximas are obtained. And let me switch to this diagram. No, wrong diagram. Hold on here. I got to open up this one. There we go. Can you see that? You can. Great. So what have I drawn here? So the black line is the path of the oscillator as it bounces back and forth. Now, technically speaking, it's one-dimensional, so this should be a flat line there, thin line. But to show you, that it moves back and forth, I gave it just a tiny bit of perspective. So, if the oscillator starts here, and it moves first to the left, passes through equilibrium, gets as far to the right, as far to the left as it's going to go, stops, turns around, and then starts going to the right, and then does this back and forth, like that, okay? So where is maximum displacement? That is, where is x maximum? Well, that's obvious. That's at the endpoints here. So x is equal to a at this endpoint here, that's the amplitude, and x is equal to negative a at the other one, because it's on the negative side. So, we could think of like positive as to the right and negative to the left. Having said that, in all of these oscillator problems, you really don't have to worry about the direction. It's not something that we ask questions about. And the reason is that the oscillator is symmetrical about the origin. So, if you say amplitude is 5 meters this side, well, you know that it's negative 5 meters on the other side. It's perfectly symmetrical about the origin. Okay, great. So we've got the maximum displacement, that is the amplitude, that occurs at the endpoints. Where does the maximum velocity occur? It occurs right at the middle. Okay, so maximum velocity occurs at the middle. And where does maximum acceleration occur? At the endpoints. Okay, so again, you need to know that, because if I word the problems a little bit differently, you want to know that if I say, what's the acceleration at the endpoints? Well, really what I'm asking for is for a max. Okay, well, that ends this problem. Let me take a look in the chat here to see if there are any questions. All right, well, it doesn't seem like there are any questions. Let me just give you these last two problems. And like I said, these are problems that you should do on your own just for practice. I'm not going to take them up unless you ask me, like during a Google Hangout, to look at them, or if you want, like if we have time next a week from today. I mean, I'm happy to go back, but I'm going to have other problems that I want to do those days. But if I have time, I can answer questions there too. Kind of make these live chats a little bit um, less formal. Okay. And so there it is. By the way, if I haven't mentioned this to you, if I'm repeating it, I'm sorry because I forgot what I told every class. But the Google Hangouts are at 7:30 in the evening. I found that a lot of people like that. Okay, but it doesn't have to be. If you can't make the 7:30 time slot, just let me know when a better time is, and we can get together. Google Hangouts are very quick. They take just a second to create, and so if you say, "Hey, are you available for a Google Hangout?" It's probably better if you say, "Are you available for a Google Hangout at a particular time?" Because I may not be in front of my computer, and then I'll probably answer yes and give you a link, and we'll go from there. Okay. So yeah, I know 7:30 is good for a lot of people, but you may be one of those people that it's not good for. Well, then don't be afraid to like ask me for a quick question. If you can catch me, I'll be more than happy to answer your questions. Okay, so here's our first question, our first practice problem. So I'm on the top of a building 40 meters high. I throw a rock up with a velocity of 30 meters per second. Probably best to say straight up, because what does a straight mean? 1D. Okay, so I throw a rock straight up at 30 meters per second. How long before the rock hits the ground? Okay, so there's the first question I want you to answer. And this will require you to solve a quadratic. Okay, it will require you to solve a quadratic. And the second question is, how fast is it going when it hits the ground? Okay, and so there's a subtlety with the second question. All right, a lot of students will say, oh, when it hits the ground, the velocity is 0. But that's not right. The way you should think of this question is not how fast is it going when it hits the ground, but how fast is it going just before it hits the ground. And the reason you want to think that way is because obviously just before it hits the ground, it doesn't have 0 velocity. It's got quite a bit of velocity because it's still falling. So it's just before it hits the ground. And the reason you want to think that way is because let me scroll back up to these equations here. These are the 3 equations for constant acceleration, okay? And they don't know anything about the ground, okay? All they know is parabola. Parabola with infinite arms on both sides, okay? And so, if you put v equals 0 here, which is a mistake I've seen happen quite a few times, where, the ball hits the ground and you go, oh, well, then the final velocity is 0. If you put 0 there, you'll get it totally wrong. So whenever you see if in these problems where you've got things that are falling, don't ever interpret like after it hits the ground. Think of it as just before it hits the ground. Okay, so just before it hits the ground, it's still on that parabola. It's still on the parabola trajectory, and so there is a velocity for that. Okay, so just be careful with that. So there's your first question. All right, you're at the top of a building 40 meters high, throw a rock up 30 meters per second. How long before it hits the ground? And how fast is it going just before it hits the ground? Okay, so there's question number 1. Definitely we'll need the quadratic for that one. Okay, number 2, an oscillator is found to have an amplitude of 1.4 meters and a maximum velocity of 25 meters per second. So this time I give you 2 of the different maximas. Maximum displacement, that is amplitude, maximum velocity. Okay, and what is the period of the motion? You go, geez, you're jumping straight to the period here. Well, spoiler alert, but the maximum displacement, the amplitude, and the maximum velocity are related by an omega, so you can get an omega, and from omega you can get the period right immediately. Okay, so that's how you get that. And then if you have 2 of the different maximum values, then you can get the third one. Okay, so the third one is what's the maximum acceleration. All right, so there it is. That ends the lecture for today. I'll wait a few minutes to see if you've got any questions before I end the live stream. And let me just remind you that the assignment for this week, I'll be taking it offline tomorrow. I can't say when tomorrow, so don't wait till tomorrow. Just let's say officially it goes offline at midnight, but at some point tomorrow it'll go offline and you'll have a new one, and for next week. And that new assignment will be for probably a couple of questions on 1D constant acceleration, and then one question on oscillators. And by the way, when I say one question, maybe I better be very clear. You can see here like how I can have one problem with many parts. Well, the way these quizzes work on Canvas is, you can have several, each part would have to be its own individual question. So when I say two questions, I probably should say two situations with multiple questions for each of them. But again, it probably won't take you more than half an hour to do it. And there's no time limit. So if you start the assignment and you have a question, don't hit the submit button. Leave it off to the side, and then get online and ask me a question. I'll be more than happy to work you through those problems. Okay. I don't see any questions in the chat. Again, I'll wait a few more seconds. And actually, I'm just going to type in the chat right now, the text chat. Everyone, okay. So if you're fine, you could just close the window, close your tab, and end the live stream. I'll just wait a few more seconds and then end the live stream at my end. Okay, if there are no questions. All right. And if you think of a question later, then don't be afraid to email me or jump in on my Google Hangout. Okay, I've got a thank you, which that's good. All right. Okay, guys, we'll see you next week. Bye-bye.